Let me share the screen with you. I hope my screen is visible. Okay, so I'm going to discuss today a topic which is very important from technical point of view, and this particular topic will be required again and again in subsequent sections of our syllabus. But before I introduce the name of the topic, I must go for a thought experiment. I am considering this experiment to be a thought experiment because this experiment is actually pretty simple, but nobody will ever bother to perform it. Okay, because the experiment looks very may look very ridiculous to persons. It's the coin tossing experiment actually I'm talking about. Who is the crazy guy who takes a coin and keeps on tossing? Okay, he's only mad guys that actually do this kind of things, or or the persons who do not have any work to do, so they can actually perform this kind of activities. But for us, it is a thought experiment. So my step number one is in this coin tossing experiment. Actually, my step number one is I'm going to toss the coin for. I'm going to toss 4 coins, and I shall write down the. I shall construct the sample space. The sample space will be constructed. Will be constructed. Okay. So tossing of 4 coins, sample space will be constructed. That is my step number one. So let me make a chart. The chart contains first column, which is sample space. And here I'm going to tabulate all the possible outcomes that may belong to this sample space. We can name this sample space to be capital S. And you know from combinatorics that when we toss 4 coins are tossed, total number of outcomes is actually 2 to the power 4, which is 16. It is only a matter of time that we want to tabulate all the 16 outcomes, and we shouldn't lose anyone. So let us do it one after another. Okay, so my first outcome, actually I will do it in a specific way. First of all, you see that I am writing that all the outcomes are heads. Then what I will do, I will make one particular head to be tail. Then I will shift the tail along the left hand side direction in the following manner. Just watch, you will understand that what I'm actually doing. I'm shifting the tail. Just look at this pattern. Number 5. In this manner, by following this manner, we are able to consider in 5 outcomes already. Okay, so this is my column 1, and again in column 3 I am considering the sample space capital S. So then after this, what we can do, we can consider all the outcomes to be tail, and we can apply similar sort of procedure to get the remaining outcomes as follows. Shifting heads now on the left hand side. So we have this, and we have this. As you can see, a kind of diagonal pattern is observed over here. Let me mark it. Just look at this particular pattern. Just look at this particular pattern. Now 10 outcomes have been tabulated. Apart from these 10 outcomes, we have 6 more. So we will try to find those outcomes also. So why am I writing column 1, 3, and 5? Because in between column 1 and 3, I'm going to put something else. Okay, so therefore I'm naming it as column 1, column 3, and column 5. Don't think that it is a mistake. Then in 11, the 11th outcome that I can take is as follows. I can consider this to be TH, TH. This is one outcome. And by following this pattern, I can write HT, HT. This is kind of one group. Now we have the third one as, 13th one as HH, TT. And then we can make it as TT, HH. 15th one, we can make it as THHT, and 16th one we can make HTTH. Now, is there any crazy student in my class who can take a coin and toss it 4 times subsequently? I don't think so, because I'm not going to do this experiment, this crazy experiment by myself. It is very crazy. Okay, but we are, at least what we can do, go for the thought experiment. So these are the outcomes which will be obtained by tossing 4 coins simultaneously or a single coin 4 times subsequently. This is my sample space. Now in step number 2, I will assume that the coins I'm working with are unbiased, or the physical system are unbiased. As soon as I actually assume this, that the coins are unbiased, then since there are 16 outcomes, we can put the probabilities here in between. All the probabilities I will write. And you know that when we consider the system to be unbiased, the probabilities can be calculated using classical definition, and every outcome has equal chance of occurrence. So in this manner, we can substitute the probability, and it is pretty simple. It's a matter of time to find out the probability, which is 1 by 16, 1 by 16, 1 by 16, 1 by 16. Let me take some time to write all the probabilities in this manner. 1 by 16. I am able to do so because my assumption is that the outcomes are equally probable, because the coins are unbiased. If I do not consider this assumption, I am not able to put 1 by 16, because I am not sure that whether it is indeed 1 by 16. That means when I'm imposing, as I told you earlier, that when I do not calculate probability, I actually impose probability on the system, on the physical system. So whenever I'm writing 1 by 16, it means that if 16 times you perform the experiments, one time you are supposed to get the outcome HHHH. You are supposed to get it. This is the thought experiment. That's why it is a thought experiment. Remember, it is a thought experiment. Okay, and if you carefully observe that if this probabilities are added, since 16 probabilities are there, so it is quite obvious that in step number 3, you calculate the total probability. Total probability in the above chart, total probability in the above chart is 16 into 1 by 16, which is equal to 1. Now, why this particular step number 3 is important? Because whenever you are tabulating something, the outcomes of the sample space, and if you miss any particular point, suppose for the time being, I have asked you to tabulate all the probability, all the outcomes, and unfortunately, you have not considered these 2 outcomes. You have forgotten to place it. Then if I do not consider these outcomes, just think, if I do not consider these 2 outcomes, then how many outcomes will I have? We will have 14 outcomes. And in that case, the total probability will be 14 by 16. But we know that probability of the sample space PS must be equal to 1. And therefore, I cannot consider, if I do not consider these outcomes 13, 14, I cannot say that I have got my sample space, because sample space must contain all possible outcomes. And therefore, we have to be very careful while constructing our sample space. For this sample space, I can consider that this sample space is exhaustive because all the outcomes have been considered. Sample space is exhaustive. I hope that you are familiar with this term exhaustive. Okay. Now, I want to do something else with this particular chart. This is my chart 1. Okay, so I want to implement something else to the chart. Okay, so what am I going to do is that let me write these probabilities, these names. You know, these are probabilities. I'm naming it, renaming it in the following manner. If my I can consider this probability to be capital P, and this capital P, and this capital P. Okay, I want to introduce another variable capital X here in this particular case, another variable capital X here. And what is this variable capital X? This variable capital X. Okay, let me write in the step, then you will understand. Step number 4, introduce a new variable, capital X, which will count the number of heads, in each outcome. This is my step number 4. So X is a variable which will count the number of heads in each outcome. So according to this, I can count the heads for each of the outcomes. For the first case, it is 4. For the second case, it is 3. For the third case, it is 3. Here it is 3. Here it is 3. Then in this case, it is 0. Then here it is 1, 1, 1, 1. And here in this particular case, the outcome is number of heads is 2, 2, 2, 2, 2, 2. Okay. Now, if I look at these particular numbers, each of these numbers are actually associated with the corresponding outcome. This number is associated with this outcome. This number 3 is actually associated with these outcomes accordingly. Okay, so we can associate to each outcome a particular number that we have defined. I'm going, just take a screenshot of this page. I'm going to the next page. Now, if you carefully observe that this variable that I have defined, X, which is actually the count of heads in each of the outcomes, okay, it is working in the following manner. I am considering the sample space S. The sample space S is being considered, which is capital S. I am choosing the elements from the sample space. I am operating the count X on each of the elements. And what I'm getting in return, I'm getting a subset or a set which consists of the following members: 1, 2, 3, 4. And you can consider this is a subset to be the set of real numbers. R is the set of real numbers, real number set. Okay, so doesn't it look like a function, that as if we have defined a function f from the set capital A to set capital B? Answer is yes. Here the function capital X is actually looks like is behaving like a function. How? If I take any element H, 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 or if you say that this is my first outcome, you just write 1. And if I apply X on it, Or if I apply x on 1, 1 means the first outcome, you find the probability, the count is 4. If I take any outcome, say HT, okay, and if I count it, count the number of heads, it will be 2. If I take any outcome like THHHH, here the count is 3. If I take any outcome like TTTTH, here the outcome is 1. If we consider the outcome TTTTT, the outcome is 0. So as if the outcomes are being taken from the sample space and the count is being operated on it, and it is giving us a value which is a subset of the set of real numbers. By looking into this scenario, mathematicians have actually derived a definition for this particular variable x. They have named this variable as random variable. I have often seen people giving the definition of random variable very in a very simplistic way. They say that random variable is a variable which is associated with a random experiment, which is a very simplistic definition, but it is not a mathematical definition. So what random variable is actually, random variable is a function whose domain is the sample space, and whose codomain or range, whatever you call, is subset of set of real numbers. So I choose a sample space like this with several points in it. X is operating on it, and it is taking us on the real number system, some part of the real line, maybe this part. It is projecting like this. So capital X is thus a random variable. Now, if I look at the random variable that I have defined over here, which is the count of head, this is not the only random variable that you can consider. Okay, apart from this, you can consider another random variable on the same set. So just like X is a random variable giving counts of heads, you can consider another random variable y giving count of tail, and you can design redesign the table, the chart, as I have designed it. Okay, and not only capital Y, you can define any variable as you wish. You can define a random variable in the following manner: that okay, I'm interested in that random variable which is giving us a count of 2 heads which appearing first, not in between and not in the last, like this. Okay, so in many ways you can do it. Okay, so whatever random variable you select, its random variable is a function which takes the element of the sample space to a number of the subset of set of real numbers. Let us analyze the chart which I have shown you over here. Let us analyze this chart furthermore. Let us define the properties of this chart. Let us talk about some properties. If you carefully observe, you will find that X is discrete. X is discrete. Why? Because X contains X is operated on 16 distinct outcomes. each of these outcomes can be noted and you can operate X on it. Okay, you can say that, yeah, this is the first outcome, this is the second outcome, this is the third outcome, and so on. Okay, so you can count them. So what is a discrete? So X, we can say that X is a discrete random variable. From this perspective, X is a discrete random variable. Okay, so what is the discrete random variable? Discrete random variable, a random variable is discrete actually. Random variable is discrete if it operates on a finite or countably infinite sample space. Sample space. Then we say that the random variable is discrete. Let's talk about the random variable time. Okay, or say temperature. So if I consider a random variable temperature, and if I say that this temperature varies from 0 degrees centigrade to 1 degree centigrade in a certain cold country, then obviously you know that I'm talking about the real number. I'm not talking about the interval 0 and 1, which is obviously not containing discrete elements. They are not finite, they are not countably infinite. You do not know where to start your counting. Okay, so this sort of random variable is not a discrete random variable. It is only a matter of having a precision device which can give me each and every temperature which can happen between 0 degree centigrade and 1 degree centigrade. So this category is not a discrete category. It is something else. So this is my first observation regarding the thought experiment that I have done. My second observation is that the probability, now we can consider the probability to be that probability that I have written as I have defined by capital P only. I can consider this probability as probability that the random variable X takes the value small x. This is my probability notation. And we observe that the probability is actually greater than or equal to 0. Okay. And number 3 observation is that if I can declare that I have considered all the outcomes in the sample space, the total probability must be equal to 1. Okay. So we have got three important properties. That is, the random variable is of discrete type. Probability is associated with this particular chart is non-negative, and total probability is equal to 1. Such a chart is called discrete probability distribution. Such a chart is called discrete probability distribution. Okay. Now the probabilities here, that is this one, these probabilities, we are actually, mathematicians have given a specific name for these probabilities. Just like if I call by the name Abhishek Gupta, you'll automatically understand that if there are no more Abhishek Guptas in the class, then I'm actually talking about the CR. Okay, so we give a name to a person to easily identify the person. Just like probability, this type of probability has been given a special name. Now, if you ask me why is it so, the answer is that, as I told you here, that this is not a discrete case, and pretty obvious that you can understand, even if I'm not saying it, this type of random variable is probably continuous. So there also you are getting a probability which is of continuous nature. Here you are going to get a probability which is comes from a discrete set of variables. So we want to distinguish between the two types of probabilities. So therefore a name is required, and this type of probability, which is associated with a discrete distribution, is given a name which is called probability mass function. probability mass function, or in short, PMF, probability mass function, or PMF. And whenever next time if I actually uttered the word probability mass function or PMF, will automatically understand that I'm talking about a discrete probability case. Continuous probability case, in continuous probability case, we call it probability density function. Okay, I'm saying it in advance. So whenever I talk about probability density function, you will automatically understand that I'm actually talking about the continuous case. So that's therefore a name is required. So these are the observations that I can make from the above chart. So we have got my point. Yeah, my today's topic was to give you the idea about discrete random variable and probability mass function. So these properties are actually very important, and just you keep this in mind. Now, if you ask me that what is the connection, in the first class I talked about the axiomatic approach, and what is the connection of this axiomatic approach to this type of probability? It is pretty obvious that in axiomatic approach we wrote probability of any event is greater than or equal to 0. Here I have written the probability of this event is greater than or equal to 0. In axiomatic approach, I wrote probability of S equal to 1. Here I have written the total probability is equal to 1. So everything comes from the axiomatic approach. It is not that something different is being taught. I have changed the name only. So this is one side of the story that I wanted to tell you and today. Okay. A second part of the story is something else. Whenever we have a discrete random variable, so how many steps we did? Step number 4. My step number 5 is, now as we have got our probability chart. Now as we have got our probability chart, let us do something else with it. Something else with this chart. Let us calculate some other mathematical let us not calculate, let us use some other mathematical tools on it. I have enabled the chat box. You can put your attendance quickly. Okay. If you are listening to me, you can put your attendance. Okay. Now let us use some other mathematical tools on the probability chart. What mathematical tools I'm talking about? In school days, you knew this particular formula that if you have a variable x and their frequency is given, then we can easily calculate the arithmetic mean using some formula. So the arithmetic mean is calculated from this frequency chart in the following manner. I can multiply each of the values with the frequencies. Okay, I'm considering the finite number of values, and the entire thing can be divided by total frequency. You are familiar with this particular formula, and this quantity is x bar. Okay, and if I do so, the same thing with the probability chart. We have the values x equal to x, and probabilities are also there. So what are the values x equal to x? Remember, here I'm not going to tabulate all the I'm not going to tabulate all the outcomes of the sample space, because now I'm not interested in each of the outcomes of the sample space. Now I'm interested in the values that will define the sample space. So when I'm talking about 0, That means I am only talking about those outcomes where the number of count is 0. When I'm talking about the outcome 1, that means only those outcomes I'm considering where the only those outcomes I'm considering where the number of count is 1, number of count of head is 1. Then I can consider 2, I can consider 3, and I can consider 4. This is the simplest version of the probability chart. When the outcome is 0, let us try to find out from the chart. When the outcome is 0, that means I'm talking about this serial number 6. The probability, and this is the only case, the probability is 1 by 16. So I can write here 1 by 16. When the outcome is 1, that means I'm talking about those outcomes where count was 1 only. So there are four of these types. So what are these types? TTTTH. Okay. So these are the types. So I can say that for x equal to 1, I can consider this case to be similar to either I am getting TTTTH or I am getting TTHT, or I am writing it as THTT, or I am writing it as HTTT. Okay. And these are mutually exclusive. So you can apply the axiom 3, probability of A union B is equal to probability A plus probability B. So here also, you see the axioms are actually playing their respective roles behind the screen. So here the probability will be how many for each of these cases 1 by 16. So 4 1 by 16s are there. 4 1 by 16s are there. So that will be how much? 4 by 16. Similarly, you can go for 2 also. How many 2 outcomes are there? For x equal to 2, how many probabilities are there? How many of these types are there? These are the types, and there are 6 types. So that probability will be 6 by 16. Just a minute. This will be 6 by 16. I'm writing here 6 by 16. For 3, that will be this one, this one, this one, and this one. So we'll be having 4 by 16 once again, 4 by 16. And for 4, only 1. So 1 by 16. So if I add them up, what will I get? I will get this 6 plus 4, 10 plus 4, 14 plus 5 plus 1, 15 plus 1, 16. So 16 by 16. Total probability summation P of x equal to x is equal to 1. Now I was talking about the arithmetic mean. Now suppose what I'm going to do is that in this particular formula, I'm going to replace these F1s, which are actually the frequencies. I'm going to replace these F1s by the probabilities. Okay, so for this particular scenario, if I suppose, and values are this x, this is my x1, suppose, and this is my x2, and this is my x3, and this is my x4, and this is my x5. 5 values are there. Only 38 people have written their roll numbers in the chat box, but I can see that 45 participants are there. Please write your roll numbers in the chat box if you are listening to me. And so if I do so, you see that I'm going to take all the values 0, 1, 2, 3, and 4. But here I'm going to multiply these values by their probabilities. So in place of frequencies, I'm considering their respective probabilities. So I'm considering 0 into 1 by 16, 1 into 1 by 16, 2 into 1 by 16, plus 3 into 1 by 16, plus 4 into 1 by 16. Just look at this particular thing. That is what I am doing over here. And the only difference is that we do not have frequency right now with us. We have the probabilities, and we are actually calculating. We're actually calculating the numerator part. The denominator, what we can do, we can sum all the probabilities together. So 1 by 16 plus 4 by 16 plus 6 by 16, as if I'm actually summing all the probabilities. But you know the denominator part is 1 actually. The only thing that you need to calculate is the numerator part. So that is 0, that is 1 by 16, that is 2 by 16, that is 3 by 16, that is 4 by 16. Okay. And if I add these figures, I will get 10 by 16. Okay, so I am calculating, I am multiplying each of the values by the respective probabilities, and I am dividing the entire thing by the total probability. But total probability is 1. Total probability is 1, so denominator part will not be there. So this is gives you the numerator part only, which is 10 by 16. This thing that I have actually calculated for a discrete probability distribution here, discrete, or you can say discrete random variable x. This quantity is actually called expectation of the random variable x, which we define by e of x, and expectation is nothing but similar to the arithmetic mean x bar. Okay, so we can do this calculation for the discrete random variable case. This session is going to end. We still have time. So for the next session you join, let us talk about, let us talk for 15 minutes at least, so that we can summarize the entire thing of today's class. So please join in the next session.